Okay, awesome. So if you just join us now, we're just waiting another minute or so here to get started, just to give people the chance to join us.
Okay, I think we can get started. It's 4:04. So, well, thanks, Leo, for accepting our invitation to be teaching this workshop, the second workshop from the AGSA, and hopefully it will be a good workshop for everyone here. So we also try to we always try to create workshops that really help our grad student life. So hopefully it will be valuable for all of us. So it's all yours, Leo.
Awesome. Thanks, Carlos. Hey, everybody. My name is Leonardo Bastos. I'm Brazilian as well, like Carlos, and I did finish my master's here at K-State back in 2014, and then I went for a PhD in Nebraska in agronomy as well, precision ag and soil fertility, which I finished in 2019. And now I'm here back at K-State working with Dr. Ignacio Ciampiti as a postdoc in his group. And when I was doing my master's and my PhD, I always really enjoy statistics, and especially the applied side of it, which sometimes is hard to really get from statisticians teaching those classes. And so this workshop that we put together is basically trying to bring some agronomic principles together with the statistical and programming principles, and hopefully give you a perspective that perhaps you haven't had in your stats courses yet. Okay, so I'm gonna start sharing my screen here so we can go through some details. So you all should have received an email from me with an RStudio project, and I want to, let me just take this out of the way. So if you're seeing my desktop here, what I did is I have this art workshop folder. I'm going to open that, and then inside of that, I have the workshop share folder, which is what you should have had from the email I sent you. I want to ask you to open that folder, and then notice how in this folder here we have 3 subfolders. One is called data. That's where all of the data that we're going to use is going to go. The other one is called Markdown, which is basically where our scripts are going to live. And then we have a third one that's called Output, which is where we're going to save anything that we want to output from our script in our analysis. So any graphics, any tables, anything like that. And then we also have this icon here, which is the workshop share.rproj. I want you to double click on this. And this is going to basically take you to the window of the project. Let me just give it a moment here to load. Hopefully yours is loading as well. So maybe my RStudio looks a little bit different from yours, but they should all have the same functionality, and that's what matters. So I just have here, well, let me do this. So on this lower side here of your RStudio window, if you come on the Files tab, you're going to see this R icon. If you're not seeing it, it may be that you have this this toggle bar just way too squeezed to the right. So if you don't see it, just drag it to the left. You're going to be able to see that icon. If you click, so again, Files tab, that RStudio project icon. When you click on that, you come to the main directory of this project, right? So which is the folder that we just saw before. So here again, we have our data, our markdown, our output. I'm just going to close the script I had there. So you were probably seeing something like this. I just want you to hit this button to go to the main folder of your project, go on markdown, and open the day1_blank.rmd. Notice how there are two files. One is HTML, one is RMD. Open the RMD. So this is going to pull up here the script that we're going to be using today. And for now, I just want to toggle this to the right just so we have more space and you guys can also see better our markdown script. So I just want to go down some housekeeping about today so you're aware of what's going to happen and we all are on the same page. So this workshop is basically 4 hours, is split into 2 days. Today, the first day, we're going to be talking about ANOVA and experimental design. Tomorrow, we'll be comparing ANOVA with regression and looking at some cool applications of regression analysis. Everybody is muted, and if you have any questions, please post in the chat. Carlos and perhaps other AGSA representatives will be then reading those questions to me. So if you have, basically, if you have any question that is like, so we're going to be coding together. So if I'm coding too fast and I bring my screen up and you can't see the code, you can just say in the chat, please, can you go back up to line? You can reference the line side, the line number here on the side. I can go back, I can do that. If you have any general questions, like something about a concept that I'm explaining, please feel free to ask in the chat as well. If you have technical issues, unfortunately, we are not going to have the time to really go through those problems. So unfortunately, we're not going to be able to help you. But this is being recorded, and we will be glad to help you in the future when this is done, and so you can get back on track. As I said on the email, if you have 2 screens, it's going to be better for you because then you can use one to watch my live coding and one for your RStudio window where you're going to code. If you don't have, you may split your screen in 2 or do some other creative thing to get around that problem. And so this is the second workshop series that we do. So we did one last fall where we went through the basics of R and RStudio, our projects. We talked about data wrangling with tidyverse. We talked about ggplot. And so for this year, we're kind of expecting that you already have some background in those topics, and I'm not going to be getting too much detail when it comes to those things specifically. And so we're kind of expecting you to have some knowledge of RStudio in general, RStudio projects, how to use our markdown, how to do some light data wrangling and use the pipe, how to do some plotting with ggplot, some Stat 705 topics, which is basically ANOVA and regression. And I just have here my blog. So I have a blog where I post some of the codes and things that I do. And I do have a few posts related to ggplot, to data wrangling, and to some of the things we're going to be talking today. So that's a resource you can always use as well. And of course, the internet is full of resources when it comes to R. So I just want to tell you that if at any point you think things got too complex, you know, you don't feel discouraged. Just if you cannot keep up anymore, we do offer all those resources that you can refer to and then come back to these recordings, and we can always help you in the future as well. So because we're not going to be helping with technical issues, I just want to give a couple of tips for you when it comes to troubleshooting code. Some of the common causes of code error is basically extra or missing parentheses. So for example, if we use a function called mean, which basically takes a string of, or a sequence of values, a vector of values, and I use the function C and to concatenate, and I just say 1, 4, 5. Notice how like we have all parentheses there. If I have a missing parentheses, this is gonna give me an error. And so this is just for you to be aware that parentheses are important when it comes to R, and it's one of the common causes. Also, it's a very common problem to have. So R is case sensitive. So if you save an object as A, let's say, if you save an object like A equals to 1, and then you try to call A uppercase, it's not going to know it is A. It has to be the exact case that you used when you created the object. So those are two of the most common issues that people find. Okay, so just very quickly touch base on some of the R Studio projects details. So we kind of already talked about it, that this is where all of your files will live within this project. If you want to go to the project directory, you're going to click on that button there, and you can navigate between the folders that we have. So data, so if I come into data, you should be seeing all this. You want to go back up to the main directory, just click again on that icon, and that will help you navigate. So we're going to be using our markdown files. I'm not going to tell you too many details about how this works, but just a few overall points that are important here. So so this is an R markdown file, right? So you see that I'm basically writing plain text where you're seeing here, and where the actual R magic happens is inside a chunk. So this here is a chunk. So the chunk is where you actually run your code and where R will try to interpret your code. Anything outside the chunk is not going to be interpreted by R as code. And R markdown files are nice because you can basically integrate comments, code, and output of that code all together consecutively in the same file. And that's really cool to have all those things together. So that's why we're using R markdown here. So we're gonna start running some code quickly here, but just to tell you, if you want to run just a single line of code within a chunk, at least on Mac, I just place my cursor anywhere in that line, and then I just hold Command, perhaps in Windows is Control, and push Enter. So it only runs that single line that my cursor was on. And if you want to run the entire chunk, you just hit on the play button, which is this one here, which is going to run the entire chunk all together. Those are some quick tips. Let's see what else. Oh, something very important that we're going to be using a lot. So if you guys see the way I'm using here, so the syntax of using the hashtag, and you're going to see down below, I'll use 2 hashtags sometimes, and even 3. This basically creates a hierarchy between these headings. And it's nice because when we do that, our Markdown is already creating a table of contents for you using those headings. So this is going to be important as well. If you see here on this upper side of the R Markdown file, there's those multiple lines kind of indented in and out. If you click on that, this is going to bring up the table of contents. So this will help you to navigate on your script. So just so you are aware of that as well. Okay, so I think this is basically the housekeeping things I wanted to tell you, and then we can just get started with what we're here for, which is talk about ANOVAs. So today we're going to be running basically 4 different analyses here. So, and we're going to be using 2 different data sets for that. So one data set comes from a well-conducted, completely randomized design. And the other data set comes from a well-conducted, randomized, complete block design. And we're going to talk a little bit more in detail about these designs in a second here. And then we're basically going to do a complete analysis, which basically follows the workflow of any analysis that I do, and I believe most people do, which is you import data, you do some exploratory data analysis. Then after that, after you have some idea of your data, you do a formal statistical analysis, look at the ANOVA tables. Based on that, you decide how you want to extract the means and do pairwise comparisons. You get the ladder separation for those comparisons, and then come up with the publication quality plots. So that's basically the workflow that every analysis has, more or less, to some extent. So we're going to do a complete analysis for the well-conducted, completely randomized design data set. And then we're going to do some 3 other analyses looking at a poorly designed, completely randomized design, and then a well-designed, randomized complete block design. And then we're going to play with the fact of treating blocks as fixed or random and how that impacts everything. All right, so you should be in this part here of your script, the setup. You may have a line here that is library broom mixed. You can just delete that line or just hashtag out because we're not going to be using broom today. So let's do this. I'm going to run one by one here just to see what happens, right? Because if we have an error in one of these packages, then you will have issues running some parts of the code later on. So I'm just going to go one by one just to make sure that here and with you, everything is loading correctly. So the first one, all right. So what I'm doing is I place my cursor on row 61. I'm holding command on a Mac and perhaps control in a PC, and I'm just hitting enter or return. So the first one, the first tidyverse ran all right, car ran all right, LMER test all right, EMEans all right, multicomp all right, midar all right. So for me, this ran. All of these packages have been loaded. And for them to be loaded, they first have to be installed. So that's why we sent you the email asking you for you to install these packages. Okay, so let's get right into experimental design. So experimental design is the part of the study that helps you to address how treatments are being allocated to your experimental material. And the way that we decide which experimental design we should use depends on basically 2 factors. The first one is the homogeneity of experimental material. So let's say you have a field study, right? And you go out there, you take soil samples, and you realize that one area has a coarser soil and another area of your study has a lighter soil. And we know how that can impact yield. So then we would probably have heterogeneous material in that sense, and we have to account for that somehow. Other types of limitations are like if you have limitations in funds, space in an incubator, size of benches, or any type of limitation that does not allow you to run an entire run of your study in homogeneous experimental material. And then two of the most common experimental designs in agriculture specifically are the completely randomized design, or CRD. I'm going to be calling it CRD from here on, and the randomized complete block design, RCBD. Now, these acronyms are very similar, right? If you think about it. So if you're not familiar with it, just try to remember or write it down somewhere. We're going to be referring to them as CRD, so the simplest one, and RCBD, the one with the blocks, which is a little bit more complicated. Okay, so the question that we have to ask ourselves then is, do I have enough homogeneous experimental material to accommodate all of my experimental units? So if you say, yes, I do have, then that means you can use a completely randomized design. What is a completely randomized design? If you run this chunk here, it's going to load this image that is basically portraying, it's like a very simple example of a CRD, where we have only one. So the color in the background, the brown color is kind of showing us soil type. So let's say it is only one soil type in your entire area, and we have 9 treatments in this case here. So we randomize every single one of these treatments, and they could fall in any of these plots. There is no restriction in randomization. So here what we see then is that treatment number 1, which for us doesn't really doesn't really matter what it is. It's just that it is the same treatment. It fell 2 times into this first column, and then 1 time on column 2 and 4, and did not appear on column 3. Now, because we are assuming that experimental material is homogeneous, this should not be a problem. It's all right. You could even have treatments even closer, and that should still be okay if you're assuming you have homogeneous experimental design. So let's run an example of this, of having homogeneous experimental design and running a CRD. So you should come to row 96, where we have the data import, and you should be seeing this. So now what we're going to be doing is loading some data. So right here where we have CRD_DF, and just to let you know, this is the part of the workshop where we start coding together. So up until now, you didn't have to code. This is where we really start coding, and we're basically gonna go together on this and build the script together. So if you can catch something, let us know in the chat, and we'll be glad to help you out. Okay, so this CRD_DF is the name of the object that we will save the data set to. So I'm going to use the get symbol, which is the less than dash. And then we're going to use the read_CSV function. Okay, so now you open and close quotation marks like that, and then have your cursor in between quotation marks. So this is one of the beauties of working with our projects. If you just hit tab on your keyboard, it's going to show you where you are. So right now, because the day one blank is saved into the markdown folder, we want to get outside of this folder and go inside the data, which is where the data is. So to get outside of a folder, we use the .. So see how now it's showing me what is on outside of the markdown folder, right? And if you are on a PC using Windows, I think the / works. If it doesn't work, you can try the /. But on a Mac, which I'm using a Mac, is /. So you hit tab, then we can just select, we want to select the data, and then tab again, we want to bring in the crd.csv file. So this is how it should be looking like for you right now. So I'm going to run this. I got some messages here just showing, just some okay messages, just showing how we parse the different columns. And now I want to run line 100 here just to print the data set. So we see here this data set has the design column, which is just saying CRD. We have a rep column that has the replication number. We have SR, which is seeding rate. And the unit here is after the underscore, so it's 1,000 seeds per hectare. And then we have yield in micrograms per hectare. And we have 20 observations again in this data set. Okay. So now let's do let's see here. Let's use the function summary on this data set. So the data set name again is CRD_DF. I'm just going to copy from there and bring it here. Let's check a summary of this. So we see that the design variable, which doesn't really matter for us, but it's being interpreted by R as character. The wrap variable is being interpreted as numerical, and it's giving us a summary here of the quantiles of this variable. It's doing the same thing for seeding rate and the same thing for yield. So it's R interpreted these 3 variables as numerical. Okay. Another way to look at this, so now I'm moving to the next chunk here that's called glimpse. We're going to use this function called glimpse to look a little bit differently at this data set. So the glimpse just shows us, again, how R is interpreting those variables. So the first one, design, is character, then all the other 3 are double, and just giving us some values for those. Okay, so we're gonna, next thing, now that we took a look at these variables, it's important here to understand how R is interpreting them. So the only one that we're really gonna have to change is the rep. Okay, so if you come down here to the wrangling chunk, we're just gonna use the get sign again. So we have to start, and notice how now I'm calling this CRD_DFW. And this W here is what I usually add to say that is the wrangled version of this data set. Now, this data set doesn't require lots of wrangling, so we're not gonna really do too much. But so we're calling CRD underscore DFW. We're bringing the CRD underscore DF, which is the one that we had to begin with. And then we use the pipe operator. So the pipe operator is basically taking whatever is on its left and using that as the input of whatever is coming on its right. And the convention in R is after you use a pipe, you hit enter to go to the next line. So we're going to use here the function mutate, and we want to change a couple of different things. So the first one is the column rep. So I'm just going to call the rep again, say equal, and then I'm going to use the function factor. So I'm going to force R to interpret rep as a categorical variable rather than numerical. And we're going to talk more about why this is important when we get to the ANOVAs. And then notice that my cursor is in between the parentheses right there. I'm going to add a comma and hit enter. And I'm going to come up here and just copy this name SRKSHA, and I'm going to paste here, but with a difference. And this is important that you follow along because this can make a difference and can cause issues if you're not aware. I'm just going to add an F in front of this because so excuse me, with rep, we're just overriding, we're turning rep into a categorical variable and overriding on top of rep itself. Now with sitting rate, we want to make it a factor as well, but I don't want to override on top of sitting rate numerical. So I'm creating a new column that I'm calling F for factor. So factor sitting rate is going to be the factor again of sitting rate. So if we just run this, so I just had my cursor anywhere in any of these 3 rows and just hit command return, and it runs it. And then I want to ask for a summary of this wrangle data set. So now we see that rep is showing like 1, 2, 3, 4. So the levels, and it's just showing how many times each one is appearing. So now R is seeing rep as a categorical variable, as a factor. And so sitting rate is still there. So it's still seeing it as numerical, but now we have this factor sitting rate, which has the levels 40, 60, 80, 100, and 120. And each one of them is appearing 4 times because we have four blocks or 4 reps. So this is where we really we should get to. Okay, so now let's plot this data. Let's look at this data and try to understand what's going on. We're going to use the function ggplot. So with ggplot, the first thing you tell it is the data frame name. So we're going to use the CRD underscore DFW, which is the wrangled version, right? And then you add a comma, you add the AES function for aesthetics, and we tell it what goes on X, what goes on Y. So I'm going to say X equals, and I'm just going to copy from above here, the F sitting rate, KSAJ, comma, Y equals yield megagrams per hectare. And then I get to after the last parentheses, add a plus, hit enter, and I want to bring here a box plot. So a geom underscore box plot. So if you just run this code here, you should see this plot. So this is just exploratory plot, so we're not going to be making this plot look nice at this point, but just so we have some idea, right? So these are the box plots which gives us an idea of the distribution of this data. And we see here as sitting rate increases from 40 to 120,000 seeds per hectare, we see that yield in tons per hectare increases up until a point and then decreases slightly. So this is the response we're seeing, right? But again, this is just exploratory. We have not done any statistical analysis yet. Okay, so once we have this plot, we kind of understand what we're expecting from our data, even before we start with the statistical analysis. Okay, so now we should get to the statistical model part of the code on row 127. So I'm not going to get too much into detail, but you're going to see throughout the script that I sent you that I'm changing here the option of the contrast that's being run. I'm not going to get too much into this explanation, but basically it is a constraint that we have to apply on the design matrix to be able to estimate the model parameters. This is not something that we are really taught that much in grad school. It's more perhaps for mathematical people that have to think more about these things. But it's just something that I want to tell you that in R, the default contrast that is used in the default matrix restriction that is used is called set to 0. And in research, we normally want the sum to 0 contrast or matrix restriction. So I'm just using this piece of code here to change the default in R, which is set to 0, to what we want, which is the sum to 0. And this is how we do it, okay? So you have to run that piece of code before we actually run the model itself for it to change. But that's just some explanation for you there. So now we can come here to the crd_mod, which is going to be our model. And for that, we're going to use the function lm. So if you're familiar with SAS, lm would be the proc glm equivalent in R. So let's just use a function here to recover our column names again. So I'm just going to copy here the dataset name, so crd_dfw, and I'm going to use the function names and put our data set in there. So it's going to show us the titles of the columns of this data set. So the way the LM works is you tell your response variable first, which is yield. That's what we're trying to explain. And then you use the tilde symbol. And now on the right side of the tilde, we add our explanatory variable, which is the factor sitting rate. And now add a comma. We have to tell the LM function where these variables are located at. So we use the data argument and we just say, crd dfw. Okay, so we can just run that. And now let's just run a summary function, but now on this model object that we just created. So what we see here on the summary function is that we have some estimates. So it estimated an intercept and then 4 more parameter estimates for this model where we had 5 sitting rates. And we're not going to talk too much about how these estimates work, but in an ANOVA setting, normally we did not really look too much into the summary function. And you see why in a second here. But we see there is a whole bunch of significant terms in this model, which is always good to see, right? Okay, so we just ran our model, right? So we ran the model with the LM function. Now, something that sometimes is not really stressed to us is that we really need to check the residuals. The residuals are the only way that we have to at least believe that our model is doing a good job in explaining our data. So we're going to use a very, very quick and dirty way of checking residuals, which is to use the function plot, and inside of it, call the model fit object, which is crd_mod. So I'm just going to go there. So this is what it should have. And if you run this piece of code, it should produce for you 4 plots. We're going to talk quickly about some of these plots. So if you just go to the first plot that it gives you is the residuals over the fit of values. And you can see that they're kind of centered around 0, and they go above and below 0 as well. So this plot here, what we want to check, the assumption we want to check is that residuals are homogeneous. So the variance of the residuals is homogeneous, basically meaning that they're kind of like spread in a cloud, that they don't really have a relationship. You don't see the residuals increase as the x-axis increase or decreases. Sometimes it could happen as well. So they're kind of like this cloud, this cloud of points, random cloud of points. That's what we want to see here. Also, this plot here helps us to find outliers. So outliers are generally, I guess people generally think of an outlier when it's either greater than 3 on a standardized residual scale or less than -3. So we don't have any of those points here. So our residuals, the variance of the residuals looks pretty good, looks homogeneous. We don't see a pattern in the residuals. We don't see any outliers here. And basically, this is what this plot helps us to see. So another assumption of the ANOVA model is the normality of the residuals. So this is called a QQ plot or quantile plot. And the dotted line is where points should lie if they're coming from a normal distribution. And this is, so we see that like our data points are kind of on this line. I mean, they're not perfectly on it, but they're not terribly out of it either. So they look okay. And then this plot, this scale location plot is similar to the first one, so I'm not going to talk too much about it. And then there's the leverage plot, which basically helps us to see if any specific observation has a strong leverage on our model. In this case here, it's pretty, everything is kind of close to zero, so we don't have to worry. So the overall conclusion from our residual assessment here is that our residuals have homogeneous variance. We don't see any outliers. They are normally distributed, and there's no influential observation. So we're good to keep going with inference. However, if any of these assumptions that we just checked do not hold for a model, then we have to take care of those problems before making inference. Because again, the residual assessment is the only tool that we have to really understand if our model is doing a good job. If the residual is telling you something is wrong, it means your model is not good. And if it will still give you means and comparisons, but you should not be using that bad model to extract means and do comparisons, because it's not a good model. So this is how we check for this. Oh, and just something else that is super interesting, I just want to quickly touch base, is that so I read and hear people saying that we should look at the normality of the data, of the raw data. And this is not very correct. So the only ANOVA assumption is on the residuals, and you only get residuals after you fit a model. So looking at raw data distribution can give you some indication that you're going to have an outlier. If you just look at the raw data and have a huge outlier already, that will probably continue to be an outlier in your analysis. But sometimes you have your raw data distribution is not directly related to your residuals, because your residuals will always change depending on the model. And you can fit multiple models to the same data set, to the same raw data. So raw data distribution is not a good indication of fulfilling ANOVA assumptions. Only residual distribution is, and that is something you only get after you fit a model. So that's just something that I wanted to make very clear, that there's usually some confusion around it.
Leo?
Yes.
We have one question from the chat. So Andrea is asking, is there a best test to do residual checking?
So we see lots of people using tests for residual checks. I normally don't do that, and it's mostly because, so the statisticians that I had as professors in the classes I took, they always made it very clear that when you do a test, some of these tests are very sensitive to some conditions, and that could throw you off. So if you just do a test and base your decision on whether your residuals are good or not based on a test, that can be misleading depending on the residual types that you have. And I've always heard from them, from different statisticians, that doing a visual assessment of our residuals is more reliable and robust way of assessing residual assumptions. So I personally don't do any tests on, like any formal tests on residuals to check for the assumptions. Okay, thanks for the question, Andrea. All right, so now let's create our ANOVA table from this model. So in R, there are different ways of creating an ANOVA table. We are going to be using the function ANOVA with the first A capitalized. And then why is that? So basically, and this is coming from the car package, just to let you know. So the functions that already are in R are either AOV or ANOVA. So these two functions here are, they basically run type 1 sum of squares. And that's okay if your data is balanced. If it's not balanced, then type 1 sum of the squares is not actually testing the hypothesis that we wanted to test. And type 3 sum of the squares is the type of sum of the squares that actually test what we want to test in research. And the ANOVA function with capital A is the only one that gives us the option of running type 3. So in summary, it is safer to just run type 3 every time, because that's gonna give you the correct answer if your data is balanced or unbalanced. Whereas if you use the lowercase ANOVA or AOV, they can be, using the type 1 sum of the squares from those functions can be okay if your data is balanced, but if it's not balanced and you forget, you're not gonna be testing the hypotheses that you think you are. So just to be safe and not to spend too much time on this, I always use the capital A ANOVA function for my ANOVA tables. So I'm just gonna come up here just to copy again the crd_mod object, which is the one we wanna use in the ANOVA. And then I just wanna say type equals 3, and then just run this. So this basically creates our ANOVA table, right? And I just wanna make a distinction here that I know sometimes can be confusing. The ANOVA table is just giving us a breakdown of how our model is partitioning variance, right? But the ANOVA table is not doing the analysis itself. The analysis itself was done on the model object. So when we use the ln function up here. So this is where the actual model is happening, and the ANOVA table is just summarizing this model and giving us a table to understand the results. That's all. So what we see here is that sitting rate was highly significant in this study. Okay, so since it was highly significant, let's extract the means. So now you can come to row 169, and we're gonna extract the means. I want to call this crd_means, and we're going to use the function em_means from the em_means package. And so the first argument we give it is the object name, and then we use the tilde to say what is the model factor that we want to extract the means over. In our case, it's the factor sitting rate KSAJ. So we just do that, and then we just print the results of those means here. So we see, so this object basically only has the levels of sitting rates, the means that we're looking at here, standard error, and then degrees of freedom, and lower and upper confidence levels or confidence limits. So notice how the em_means only gives you the means. So the model means, right? So now if we want to add the letter separation, do pairwise comparison on that, and adds the letter separation, we have to do something else. So you can come to the next chunk here, which I'm calling crd_CLD. That's kind of a crd_CLD. And then we're going to use the function CLD for compact letter display. This is what it stands for. So the first thing we call here now, it's not the model object, but the means object, which is crd_means that we created right above. And so we can just run this and print it, okay? So you can see there what is, now you can find this dot group column here, which has 1, 2, 3, 3, 4, and 4. So basically behind the scenes, it did all the pairwise comparisons, it compared them individually, it assigned the different numbers, in this case, it's not letters yet, different numbers to them, and created the grouping for us. And here just saying that use an alpha of 0.05 and use Tukey as the adjustment method. So I just want to come back here to the CLD function, and I want to add a few arguments. So something that we're seeing here is that the lowest mean, which came from the 40,000 seeds per hectare treatment, is first. So this is A. I personally prefer to have A as the highest, but this is just personal preference. But so I would come here on the CLD function and just add the argument reversed and say equals T for true, capital T. I also want to show you, like, if you don't want to use Tukey, right? So Tukey is an adjustment that is making it harder for you to find differences. which is okay, right? So, like it is a way of controlling type 1 error. That's a good thing to do. But some people don't do it. Some journals don't expect you to do it. So I'm just going to show you, if you don't want to have any adjustment, you would come here, it would say adjust equals open quotation marks, none. So this is just not going to use an adjustment. And also, I don't like the numbers here. I actually want to have letters. So for that, it has an argument called letters, and note how the L of the argument is uppercase. And then, so uppercase L letters, and then we say equals to letters all lowercase, because letters all lowercase is actually an object in R that has a list of lowercase letters from A to Z. I just want to rerun this and then again print this object. So notice how some things that change, right? So now the A, no, well, so first, we don't have any more the numbers. They're all letters now. And also the first level is the highest mean, which came from the 100 kilos, 1,000 seeds per hectare treatment. So it inverted this order, and that was because of the reverse equals true. It changed numbers by letters, which is what we wanted, and did that by the letters equal letters argument and specification. And also notice how it doesn't say that it used an adjustment, which basically means it did not do an adjustment because we asked none in this argument. So that's kind of what I wanted to show you. Excuse me. Okay, so now let's create a, oh, you know what, something else, sorry. Let's just come back here to the COD object. I wanna get to the end of this parenthesis here, add a pipe, and I wanna use the function as data frame, because up until here, this is not a data frame, and I want it to be a data frame so we can use to plot. And also, I want to add a pipe after the as data frame, hit enter, use mutate. I want to create a new column called letter. I'm going to say equal, and I want to use the function trim ws, open parentheses. So trim ws means trim white space. What does that mean? So if you look right now, this column here, you see how the letters are staggered, right? And this is by default, the COD function does it just so visually we can see that when something is different, it goes to the right a little bit. This is nice if we're just looking as a table, but if we want to plot these letters, it's not nice to have all this extra white space here. It's gonna make things look weird. So I just want to remove this white space right now. So we do that by doing the trim ws function on the dot group column. So we run this, it should run all right. And then if we print this, notice that now it is a data frame, right? So we have our treatments here, the means, the model means, center error, the group is still there, and then we have the letter as well.
Leo?
Yes.
We have a couple of questions from the chat box.
Yeah.
So the first one is, what does intercept tell us, and should we report the intercept?
Okay, so the intercept on the ANOVA is basically the well, it kind of depends on the matrix restriction that we use. In this case here, the intercept, well, the way that it's showing this ANOVA is basically just the overall mean of the model. So if you have done any design of experiments class, and if you remember creating like your ANOVA table by hand where you have your source of variation, degree of freedom, and then if it's random or fixed. Normally, we have like an overall mean row in there. So basically the intercept is the overall mean of the model. That's what it is. But so this is important when we're doing regression, right? So regression is, the intercept has an actual meaning here. But when we're doing ANOVA, especially in ANOVA where we had an effect of the treatments, the intercept is just, whenever we ask for the means from the model, behind the scenes, the matrix math that's going on knows how to use properly the overall mean and how to adjust each treatment above or below it. So we don't have to think about it. So in an ANOVA setup, the overall mean is really not very meaningful. So let's say if our sitting rate was not significant here, so this, if this p-value was like 0.3, let's say, highly insignificant, then you could say, well, sitting rate has no effect on yield. And then what you can extract from this model is basically the intercept, which is the overall mean of all the yields, which are not affected by your explanatory variable in that case. So that's the only case where an ANOVA model, where the intercept from an ANOVA model has an actual meaning for us when your treatments have no effect and you want to extract the overall mean of the model. But other than that, we really don't use the overall mean of a model, especially if your explanatory variables are significant, not directly, right? So that number and that significance is still important and is still used behind the scenes when calculating the other treatment means. But we don't have to think about it or even worry about it in an ANOVA setting. You have one more question, Carlos, you said?
Yes. Andre also mentioned we should have the multi-comp view package to be able to see the pairwise comparison, which is true.
Yes.
Besides the multi-comp package, we have to have the multi-comp view package. And then our question is about, is there any maximum number of treatments for a pairwise comparison?
There's really not. I mean, you know, if you, let's say if you have, I don't know, 20 levels on your treatment, like we had 20 sitting rates, which is, I mean, is not something that people would do, but let's say we did, right? We would still be doing all possible pairwise comparisons if we just ask for CLD like we did. And there, I mean, and that's kind of where it starts becoming more important to have some control over type 1 error, like having a Tukey adjustment, because then the more pairwise comparisons you do, the higher chance you have of finding a difference when that difference is actually not true. And that's what the adjustment does, right? But I mean, to answer directly your question, there is really no limit of number of pairwise comparisons that can be done.
Okay, thanks.
All right. Okay, so I think we stopped right here, right? So just to let you catch up. And now we're going to basically use this object CRD_CLD to plot, to make a final plot of this analysis, right? So we're going to start with a ggplot. We bring this data set here, which is the CRD_CLD. We start the aesthetics function. Now on the X, we want to have, again, that factor sitting rate. And on the Y, if you think about it, now we don't have a column saying yield anymore. That has been turned into this EM mean column, which is the model marginal mean calculated. Well, it's the marginal mean calculated by the model. That's kind of what it is, right? So this is how we get to it. And now I just want to show you something a little bit different. So so now we don't have a box plot anymore, at least not in this data set, right? So this data set has one mean, one standard error for each treatment. So we cannot really use a box plot. It wouldn't make sense. So one option we have is to use the geom_point range. So when we select this, you can use your AES function inside of it. And then we can say if you, so it has an argument called ymin, like that. We can say ymin. So imagine that we're going to have a plot where each one of those treatments, each one of the means is going to be a dot, and then we're going to have a whisker going up and a whisker going down based on this SE column. So that's basically what we're telling it, where the ymin, the minimum on the y-axis should be. So it should be EM mean minus SE. And this EM mean and SE are columns in this data set. And then after that, you add a comma, you say ymax equals EM mean minus SE. And that's it. So if you run it, oops, sorry, ymax should be plus SE, not minus.
Yeah, plus XE.
There you go. So we have the mean and then plus minus the SE of the model, right? So what if we actually want to add the letter separation to this plot? We come add a plus at the end. We use the geom_text. With inside of that function, we use the AES. And here the geom text has an argument called label. So label is basically the column name that has whatever label we want to show in the plot. And that is the letter. So we just say label equals letter. And if we do this, you don't have to run it yet, but I just want to run and show you. If we do this, the letter is going to be right on top of the point, which we cannot really see because they're both black. So I just want to, inside of the AES function of the geom text, I just want to say y equals e in mean minus 0.5. So it's basically bring the letter a little bit a little bit lower than the mean, so we can see both. So this would be a plot that you could show in a publication. I mean, the beginning of a plot you would show in a publication, right? We're still, if this were to be a publication ready plot, there's still a lot of stuff we would have to play around to make it look nice, but the content is there, right? We have the means, we have the errors, we have the letters. Awesome. Okay, so this is basically the well-conducted CRD analyzed properly, right? This is the example that we just finished here. And now what I want to show you is another case. So let's say we have heterogeneous experimental material. Well, you know what? Before I start this, let me take a step back. Let me get back to this plot and just, Carlos, if anyone has a question about something we've done up to this point, this would be a good place for like one question, perhaps.
Okay, so we don't have questions about the about the Gplot but we have one question about ANOVA. How
Okay.
can we run unbalanced ANOVA in R?
Okay, so the LM function, I mean, you can run unbalanced ANOVA the same way, right? You're still gonna, the only thing is that the model will know you have missing data and is gonna try to still model that missing component of your data. Still gonna try to give you model estimates, even if you have missing data. Now, of course, it depends a lot on the degree of missingness that you have. And if you have like 1 or 2 points that are missing, that's probably not going to be a huge deal. What you're going to see is the means of the specific treatments that have missing data. Those means are going to have a larger error than the means of the treatments that have all the observations. And whenever you're making a pairwise comparison between treatments that have missing data, that error is going to be a little bit wider as well. But R still handles it. I think that LM handles it, but it's perhaps not the best way, especially if you have more complex models. So if you have more complex models with missing data, you really want to try to use LMER, which is a function to run mixed models that really helps you more with handling missing data and how to properly assign the correct errors to missing and non-missing treatments. So, I mean, you know, short answer is it's okay, you can run with missing data, but if you have more complex models than just what we're running here, it's safer for you to run that model with a mixed model where you're going to be able to allocate better where that missingness is impacting. All right, I guess we're going to keep going then because I am behind schedule. Okay, so now so what we just did was a data set that came from a CRD in the field that was actually it was homogeneous material. We conducted this study, we got the data with very little variability because of that homogeneous experimental material, and we just analyzed it, right? Perfect. Now, what if you have this situation? So now let's say that the right side here, the darker color is a finer soil texture. So let's say it has more clay, and the left, sorry, I'm actually getting my right and left confused. On the left, you have a darker color, so a finer soil texture. On the right, you have a lighter soil color, so a coarser soil. And we know that affects our yield very potentially. And we still do a CRD. What is going on here? Now notice how treatment one, that before it didn't really matter where treatment one went because it was all homogeneous material. Now we have heterogeneous material. In treatment one, 3 of the 4 wraps of treatment one are within the darker soil texture, and only 1 is within the lighter one. If in fact soil texture will have an impact on our yield, this will be a bad design, a bad study, and bad data is going to come out of it. And why is that? Because you can see, and this is just one of the treatments, right, that we're highlighting here. If we were to do this analysis for all the 9 treatments, we would find many unbalancing in relation to how many times a treatment appears in the darker color and in the lighter color of this experiment. It would be very unbalanced for all the treatments, which basically means that your treatment means are going to be biased. So they're not going to be the most unbiased that you could have had if you had a proper design. And your errors are going to be inflated because now you have so much variability in yield that is coming from the soil texture, and you're not explaining that in your model anywhere. It's all going into the seeding rate effect, right? So this would be a bad CRD. This should not have been a CRD, but we're going to analyze as such, just so you see what happens, okay? So now we're going to bring in another data set. So you can come to the chunk on row 213. We have RCBDDF. And we're going to use, again, the read _ CSV function. Again, open and close quotation marks, have your cursor in between them. You can type .. and hit tab, go on data, hit tab, and then let's bring the RCBD CSV. So we bring that in, we just printed. So now this design is RCBD. And so both of these data sets were data sets that I simulated. So I know that they are, I have myself inflicted a higher degree of variability based on blocks on this data set. And you're gonna see that in a second when we actually plot it, okay? So let's just check the summary of this. So we see again that R thinks the wrap is numerical, and we know that because it's showing the quantiles of its distribution. It's seeing seeding rate as numerical as well, and yield as numerical. So if we use the glimpse function, it gives us that same impression as before, where it shows the variable types and just some of the first observations within each column. And now let's do wrangling. And I want to call this data set CRD bad _ DFW, just so we know that this is going to come from a CRD that was poorly designed, and how that impacts the actual analysis results. Okay, so we're going to start here with that data set. So our CBDDF, we're going to use the pipe operator. We're going to use, so this is something that we did up above. I don't want to go up and copy and bring back because I think it's going to be too confusing to know where you are. So let's maybe just try to write it ourselves. So wrap equals factor wrap. We put our cursor in between the 2 parentheses, hit enter. We do the F seeding rate. So the seeding rate is right there. We can just copy that. F seeding rate equals factor seeding rate. So this is our very, very short wrangling for this data set. And then we check the summary again. So now we see that we have, again, 4 wraps, and each one of them appear 5 times. We see the factor seeding rate, again, has 5 levels. Each one of them appear 4 times. So this is what we really wanted to see. Okay, so let's do some exploratory data analysis. Let's look at that same plot as we did before with the box plots. However, now for this case of the data that should have been an RCBD, but actually was designed as a CRD. Boy, look at those box plots. Oh my gosh. If you want to have some idea of so the box plots are just summarizing the data points. But if we actually want to see the data points themselves, we can just come back here to the box plot, add a plus, and say geom _ point. If we run that, actually going to see the data points that are given rise to these box plots. I mean, look at that. I mean, one treatment is ranging from, let's see, this is probably like around 7 all the way to like, I don't know, 17 micrograms per hectare. And these numbers are really high. I mean, this has to be a really good corn to get all the way up to that level of yield. So maybe, you know, there's something very, very variable about this data set that we are going to analyze as if it were a CRD. But just keep this in mind, it has such a large variability that is coming from the fact that it should have been blocked, but it was not, which is what we were showing up on this figure. It should have been blocked, but it was not. It was still run as a CRD. Okay, so let's run that statistical model again. So we run that options part, and then the model is basically the same as we ran before. So we're going to use the lm function. Let me again call the names. Well, let me first copy the data set name. I'm going to come down here, use the function names so we can look at the column names, and then it's going to be easier for us to just copy and paste. So the yield is going to be the first thing in this formula, and we use the tilde, and then the factor sitting rate comes after, and then we just say data equals this up here, which is the CRD bad underscore DFW. Okay, so we just run that, and then let's look at the summary. Oof, look at this. I mean, I don't know if you recall, but all these were significant when we had the CRD data. The good CRD data analyzes CRD, and now look, only the intercept, so only the overall mean is significant. Nothing else is, and this is coming because of that high level of variability that we should have blocked, but we didn't. Okay. So let's check the residuals now. So CRD mod can come here, check this. So let's go to the first plot here and see. So we don't see a pattern on the residuals, but look at the magnitude of the y-axis. It's going from -4 all the way to almost 7. So there's some very, very large outliers, and they are being, so the thing is, they are outliers here because there is a lot of variability that is not being explained by anything else. It's just everything going into the sitting rate factor in the model. So this is why we have such large residuals. And we see our QQ plot. I mean, it's kind of looking not super good, right? I mean, I would think of doing something about this data set before actually using this model to make comparisons, to extract means and make comparisons. And then on the leverage, I mean, there's nothing that's really pulling the data in a different direction. There's no highly influential observation. It's just that it's a highly variable model, right? Sorry, a highly variable data set, and our model is not being able to accommodate all that. Okay, so our model name is here, CRDBAT underscore mod. We're just going to extract the ANOVA. Let's see what the ANOVA is going to tell us about this model. Type 3. Whew, look at this p-value. It's like 0.6. It's like highly, highly not significant, right? You would never really extract means from this. So this is the point where you come to the ANOVA and you say, all right, this is where we're just going to extract the overall mean. This is where the intercept would be the only thing we should have been extracting from here. I will show you how the means are, so I will extract the means and do the CRD just for you to see what's happening. However, that is not what we should have been doing in a model where the only explanatory factor is so non-significant. Okay, I just want to make that clear. The next means and CLD that we'll do should not have been done in an actual analysis that you're reporting somewhere, but I will do it just so we can compare to the previous ones. Okay, so for the EM means, the same thing. We're just going to use the EM means function, and then we give the name of the object that has the model, and we use that tilde factor sitting rate. Just do that, just print it. So the means are there. We don't have the letters yet. So let's just now extract the means. So we need that COD. Oh, sorry, not the means, but the letters. We're going to use the object with the means. I want to say reversed equals true, adjust equals none, and letters equals letters. And then again, I just want to make this as data frame and just do that mutate, create the column called letter with lowercase l, and use the trim white space function on the dot group column. So this is basically the same that we did earlier. It's just doing again here and then printing here. So look at that. All the letters are A's, right? And again, this is not something that we would have extracted these means and asked for the letters from the pairwise comparison, because the ANOVA was non-significant. So we should have stopped there, but we just went ahead just for comparison reasons. And now let's again create this plot here. So we're gonna use that same object, the CRDbat_CLD. Gonna use ggplot and paste that object name there. Gonna use the AES. So again, on the X, we wanna have the factor sitting rate. On the Y, we wanna have the EM mean. And then we add a plus at the end, hit enter. We're gonna do again that geom point range. Geom point range. Do the aesthetics function again. We're gonna say again, Y min equals EN min minus SE, comma, Y max equals EM mean plus SE. And we can just plot it. Boy, look at those error bars. Oh my gosh, so much variability. That is just crazy. And if we were to add the letters, I'm not going to do it just to save some time, but we already know the letters would have been all A's because they're there, right? So this is an example of a very poorly designed CRD. This should not have been done as CRD. It should have been an RCB, a randomized complete block design, where the blocking factors would have been the soil types. And because we had a poor design on this heterogeneous experimental material, there's nothing we can do at this point. We can just say, it is what it is. Let's try again next year. That's it. Okay, so this would be a good point if people have, for like one question, Carlos, if people have a question about this.
No questions in the chat.
Okay, perfect. So either that means you're being able to follow me, or it means that I lost you all. Hopefully it's the first option. All right. So so then what should we do, right? Like what would have been the right thing to do? I'm sorry, you don't have to go up, I just want to go up to show you. What would have been the right thing to do here? Well, the right thing to do here was to run an RCBD, okay? So what would an RCBD look like? And what is an RCBD? So we see here that each block is a replicate. So now RCBD is randomized complete block design. What does that mean? It means that your replications are gonna happen in blocks. So for a block to be a true complete block, it has to have each treatment appearing at least once inside that block. And that's what we see in this example here, where each treatment is appearing once per block. And and the way that we randomize an RCBD is different from a CRD. So if you remember, with the CRD, like a treatment could fall right next, like right in the neighboring plot. You could have two same treatments. And that is not going to happen with the RCBD, because now we are actually conducting 4 separate randomizations, one for each block. So you take all of your treatments, you have your hat with your papers and all their treatment numbers in them, and then you're going to say, all right, for plot 101, and then you take treatment 6. and you only in this hat with the papers or in a computer that you're simulating, you're going to have a treatment appearing only once per block, and all treatments in all blocks. That's kind of what the RCBD is. And because of this restriction in randomization that we have, we see that now treatment 1, for example, which is what we're highlighting here, is appearing only once per column, where each column is a block. And because of that, it is appearing the same number of times in different soil types. So now we have another variable in our model that is the block, that whatever variability there is between blocks, it's not going to be just sitting in the model without being explained. It's actually going to go into that block, the block effect. So the block effect is going to suck for it all this extra variability in our model, and it will allow us to do comparisons that, even though there is high variability, but that variability now is being explained by the block. And so we can actually place this variability into the block term and then focus on the treatment side and still be able to conduct unbiased and low variance types of comparisons in our model. Okay, so the data set that we're going to be using here is the same data set that we used on the step above. So when we did the bad CRD, so a CRD that should have been an RCBD, we're going to use that same data set, which has a huge variability, just to remind you, which is this data set here. We can just come lower here, and you should already have the code for the light wrangling we're doing, so we don't have to retype that. Again, I just want to print the box plot of the data variability. So it's the same variability as we had on the bad CRD. It's just that now we're assuming that the study was properly planned and as an RCBD, and it will be analyzed as such. Okay, so what is the difference now in our statistical model? So we can come here to our statistical model on the RCBD_mod, and we're going to again use the LM function. And again, I just want to call the names of this object here, just so we can, so names of the RCBD_DFW, just so we can copy and paste into our formula. So we have the yield, tilde, factor seeding rate. So I just want to stop here, and I want to call your attention, right? So this formula that we're seeing right now is the formula that we use for the CRD. And this is something that when I was taking different experimental design classes, one thing I always asked myself and asked the instructor was, okay, but I know it is a CRD, or I know it is an RCBD, but how do I tell the model that a CRD is a CRD and RCBD is RCBD? How does the model know? So the only difference in the model specification is that we're going to have a plus and we're going to have the rep. That's the only difference that's going to be. This plus rep, in this case, rep means block, is the only difference from a CRD and an RCBD. So just include the comma, say data equals the RCBD_DF, _DFW. And I just want to quickly double check something here, that the rep should be a factor, just to remind you. So FCTR, when we just print the data set, it means the rep is a factor, and that's what it has to be for this to work properly. So we just run that model. You ran all right. Let's ask for a summary. Oops, I had a typo there. Summary. Wow, look at that. So before we did not, so when we did the bad CRD, we did not have rep, right? So it was kind of like this, and none of the seeding rate treatments were significant. Now they're all significant, and then there are some block effects that are also significant on the summary function. But again, on the ANOVA, we very rarely use the summary function. We are really interested in the ANOVA function and on the means based on the ANOVA. So let's just Well, next, let's check the residuals, right? That's really important. We should be doing that all the time. So if we just use the plot function to have the residuals plotted. So I don't know if you remember, I'm not gonna go up to not get you confused, but if you go up and you check the residuals of the bad CRD, remember that the magnitude here was like 8 and -4, I think. Look at now how it changed. And why is that? It basically means that all that extra variability in the residuals that we were seeing on the bad CRD now is being explained by the block effect. And that's why it's not being reflected on the residuals. And so this, I cannot stress this enough. The raw data is really not what we should be looking at when we're trying to find the best model, because the raw data is fixed. You're always going to have the same raw data, but you can apply many different models to the same raw data, and each model will give you a different residual. And the residual is what we look at when we're trying to do checking for model assumptions. So I really want to stress this because it's really something that has to be said. So now we look at the normality. I mean, it still has some kind of lower than expected and greater than expected on the normal QQ line, but I mean, it doesn't look terrible, to tell the truth. Especially like, so we only have 20 observations. So as you start increasing your number of observations in study, then it's easier to really say if they're normal or not. But when you have a limited number, like this doesn't look that bad for only 20 observations. And scale location is similar information to the first one. And then the leverage, I mean, we see again, they're all kind of around 0. So there's no single observation that's playing a highly influential role in the model parameters. So this is great, right? So we can keep going now. We checked our residuals, everything looks nice. So let's use that ANOVA function now. We call the RCBD underscore mod and type 3 sum of the squares. Look at that. So now we see the rep is highly significant, which we were kind of expecting because we had such a high variability from block to block. But because we were able to assign all that extra variability to something, in this case to block, now we were able to regain the power of finding treatment differences in the sitting rate treatment factor. So that is awesome, right? That's the role of the RCBD. You know that an RCBD has been properly used when your rep or your block effect is significant, because it means, yes, you did have all the variability and you placed your blocks in the correct orientation towards that variability to control for it, and you were able to suck all that extra variability into the rep effect and leave your treatment effects to really come to light. Okay, so let's extract them. Yes.
This is Adrian. May I ask you to tell the guys what happens when you apply a block design when you don't need to do that? I mean, with the degrees of freedom.
That's a great point. It's something that I was gonna talk more in the end, but this is just as perfect as a moment. So if you think about it, there's kind of like a matrix, right? So you have like, you ran a CRD and you should have run a CRD, or you ran a CRD, but it should have been an RCBD. So there's like, well, this is going to get too complex to not be able to draw. But basically, let me make that simpler in words. If you planned and conducted a CRD, but it should have been actually an RCBD, then there's nothing you can do about it, right? It's the case that we just saw above. Like, your treatments have a high variance, possibly, right? If your material was actually heterogeneous, they have high variance. You're not going to be able to find treatment differences, and you didn't block, so the block wasn't there, right? So there's nothing you can do. So you ran a CRD, but it should have been RCBD, nothing you can do. If you ran an RCBD, like we did here, however, your block effect comes non-significant, it's not hurting you really, like is not hurting that much, but you could have done better. And why is that? If your block effect comes non-significant, it means that you don't have that background variability that you thought you had. And if you knew that before you actually ran the RCBD, you would have treated that as CRD. And now what's the difference, right? The thing is, if you do block, but you didn't need block, you are taking up degrees of freedom to estimate the block effect. And if you did not need those blocks there and you didn't have those blocks there, then it means you would not have this block effect in your ANOVA. And those 3 degrees of freedom that we used to calculate the rep estimates would have gone to your residual degrees of freedom. So in that case, you would have more degrees of freedom in the error, which would give you more power to find true differences. So I know that can be confusing just in words, but think about it like, if you didn't have to control for variability because that wasn't there, then you would not be consuming 3 degrees of freedom in the block. And that would have gone to the error degrees of freedom, which would have made your error. So the more error degrees of freedom, the better for you. That's gonna, when you do the ratio on the mean squares, it's gonna make your error smaller, which is good because then it's gonna help you to find treatment differences better, or it's gonna make true differences be able to be found easier than when you're consuming degrees of freedom from the error, right? So basically returning those 3 degrees of freedom to the error and making your study more powerful in finding actual differences. So if you did a CRD, but it should have been an RCBD, there's nothing you can do. That's maybe the worst condition because your study now is really bad data and there's nothing you can do about it. Now, if you ran an RCBD and your rep comes out non-significant, it means you did not need those blocks. And we're still going to be able to find treatment differences if they're there. But next year, if you run the same study on the same area, just do a CRD that your model is going to be more powerful because you're going to have more degrees of freedom in the error to find those differences. I know this can be a little bit confusing, and but hopefully I was able to kind of give an idea of what happens. Is that what you had in mind, Adrian?
Yes, Leo, thank you. Yeah, it was mainly because sometimes we know that we apply blocks and sometimes we don't know if we need it, if we need that design or not. So, and sometimes, exactly. I mean, it could be a trade-off with the degrees of freedom.
Exactly. Perfect. Mm-hmm. Yes. Well, thanks for bringing that. It's definitely a very, very interesting discussion. Did anyone else have something to say? Okay. Well, I'm going to keep going here because I don't want to keep you guys for too long. Okay. So we got back to the means now. Hopefully by this point, you guys are getting used to repeating the same code. So to extract the means, we're going to use the ENMeans function. Just to recall, the model name is RCBD_mod. And then we're going to use the tilde to say what we want the means over, and it's the factor sitting rate, right? So now I got the means, I printed, and we got the means here, and we see, so I'm not going to go up there right now, but when we finish this, I would encourage you to kind of like compare these errors with the previous ones and see what's going on. But right now, this error here is a lot less than what it was on the bad CRD. Okay, so let's get the letter separation here for the for this model. So we use the CLD function. We're going to use that RCBD_means object, and I'm just going to do all the reversed equals true. If you guys don't want to do that, like you don't really have to do it right here. I just want to do so I follow my my system. But if you don't do it, you can just copy and paste from above after we're done, so you don't have to worry about it. So I do that, I do as data frame, I use the pipe, and I do again that mutate. I call the column letter equals stream white space on that dot group column. Okay, so look at that, look at these letters. They're basically the same letters that we got from when we ran the CRD, the good CRD, the CRD with little variability. So, and then you can kind of see how, well, let's make the plot, and then we'll talk more about the implications. So for the plot, I just want to copy this RCBD underscore CLD. We're going to use the same thing as before. So starting with ggplot, using the data frame name, using the aesthetics function, saying x equals to factor sitting rate, y equals to EM mean. Then we go to the end, add a plus, use the geom point range, open the aesthetics. We say y min equals to EM mean minus SE, y max equals to EM mean plus SE. And then now, because we have actual differences, I want to add the label for the letters. So that we do that using geom text, use the aesthetics function. We say label equals letter. And just to offset a little bit the letter from the actual mean so we can see it, we just say y equals EM mean minus 0.5. So look at this. I mean, this is just mind-blowing, right? So remember that these results are coming from a highly variable study, highly variable. And the reason why we were able to get such a small errors around the means and still be able to find the differences is because we blocked, and we blocked effectively. We blocked correctly in this study. And all the variability went into the block, and we were able to regain the power of finding treatment differences. So this is where an RCBD should have been used, and it was used, and we see the results, right? Okay, so oh yeah, we got enough time, awesome. So what happens then is this discussion. So if you were conducting field research, or even, I mean, it doesn't have to be field research. If you're doing any research in ag where you're using blocks, I am 100% sure that you ran into the issue of, should I treat my blocks as fixed or as random? And this is a very interesting issue that I want to show you what happens with this data set when we run them, and we will discuss what we should do in fact. So some general guidelines for when you should consider whatever treatment, whatever model factor, but in this case we're talking about blocks, right? So how should we think about if we treat it as fixed or as random? So number one, does it represent, is it a sample of a larger, well-defined population? In this case, a population of blocks. Normally, in ag, it is not, right? It's not like you went to a 2-acre field and you thought, I could fit 100 blocks here. Let's just randomly pick 4 of all the 100 possibilities, and I will run my study in those randomly chosen 4. No, it doesn't work like that, right? You go to a field, you have your blocks side by side. So maybe they are a sample of a population, but they're not a random sample of population. So normally the answer to that in agriculture is no. They're not a random sample of a larger, well-defined population of blocks. And then the next question that we should be asking is, how many levels do we have? So there are some papers saying that we should have at least 14 blocks if we really want to treat it as random. And why is that? It's because for you to accurately estimate a variance component, which is what happens when you have random blocks. You're estimating a random component of the block. For you to accurately estimate the variance component, you should have at least 10 degrees of freedom going towards that estimation. If you have less than that, then you're probably, you can still do it, right? Let's say we have 4 blocks, we can still treat block as random. And the only thing is our estimate of variance using 3 degrees of freedom in this case is going to be less accurate than our estimate of a mean of those blocks. So we can estimate actually means with less degrees of freedom than we can variance components. So we estimate means when we treat as fixed, we estimate a variance when we treat as random. So how many levels? Do you have more than 10 levels? Normally, I mean, my studies and most of the studies that I see from people in ag, they do not have more than 10 blocks. They usually have 3 or 4. That's kind of the rule, right? So in our case, let's just think about it again. Does it represent a larger sample, or is it a sample of a larger population of random? Is it a random sample of a larger population? Normally, it is not. Does it have more than 10 levels? Which means, do you have more than 10 blocks? In our case, we do not. So in that case, the recommendation would be to treat it as fixed, which is what we just did above. So all this analysis here, we treated blocks as fixed. But let's just rerun this analysis, treating blocks as random, and let's see what changes. Like, okay, so if you shouldn't do it, why shouldn't you do it, right? Why should you not treat blocks as random? Like, what is the implication, right? So let's get at that. So the data set is the same as we used before. So we've been using the data set for the 3rd time now, the same data set, just so you remember that is the same level of variability, so a high variability. Just got the summary, I mean, basically the same. So we're not gonna spend too much time there. Just gonna print here again that box plot with the wraps, so you can see again it is that same data frame with large variability. And now let's run the model. So now we cannot use LM anymore. Why is that? LM, just like ProcGLM, if you use SAS, can only incorporate one error source in the analysis. So we can only estimate one variance component, and that is coming from the error of the model, right? Every model has the minimum amount of error components that a model can have is 1, which is coming from the error of the model. Now, if we are going to treat blocks as random, the blocks themselves are going to have their own error component or their own variance components. So in this case, this model will have to be able to handle 2 error components, one from the residual, from the error of the model, and one from the random effect of block. So LM and ProcGLM cannot handle more than 1. So now we're going to use a function called LMER. So LMER is actually a function from the package LME4. However, I asked you to install the package LMER test. The only difference there is that the package LMER test uses the package LME4. However, package LME4 does not give you p-values. And it is something that the authors of the package did by design. And the package LMER test adds those p-values for you. So that's basically the only difference. If you were not able to install LMER test, you can use the function LMER from the package LME4. That would be okay. You may just not have p-values output on your summary in ANOVA. Okay, so, and also LMER, the function LMER would be the equivalent of proc mixed in SAS if you work with SAS, just so you know. Okay, so I just want to come up here again, copy the data set name because I want to use that function names to retrieve the column names of this data set. So we're going to have, again, very similar formula, right? So yield tilde factor sitting rate plus, and here is a difference. So in LMER, how does the model know if you want a given explanatory variable to be treated as random or as fixed? So if you just say the name of the variable like we did, excuse me, as we did here, then it will treat it as fixed effect, which is what we want for our treatments, right? Normally our treatments are fixed effect in agriculture. Well, perhaps, I don't know. I don't do too much genetics work, so I don't know, maybe genetics you would. But anyways, I'm not gonna get into that because I don't know what I'm talking about. So, so our seeding rate is gonna be fixed. And then we want our rep, in this case, our blocks, to be random. In LMER, the way that we do that is you open parentheses like that, you place a 1 in there, and then you use the vertical bar. And then after that vertical bar, you say the name of the variable that you want to be random. So this is the notation that we use in LMER to say that we want the rep to be random, okay? And then we just add comma, we say data equals, oops, equals this. So we run it. Let's get the summary here, just so we can see what is going on. Well, I'm just gonna leave this line here just for like 5 seconds, just so in case somebody needs to catch up, I'll give you 5 seconds. Okay, so let's look at the summary of this mixed effect model. Oh, that's also something I have not used this name before. So because this model has fixed effects, which is the sitting rate, and random effects, which is the block, the rep effect, it is called a mixed effect model, right? Whereas before, up until this point, we were only running fixed effect models because they only had fixed effects in the formula, and the only variance component was coming from the model error term. And now we have another one, as we already said. So this is a mixed effect model. Okay, so something to notice here on the so now we have this random effects part of the summary, where it's telling us that the standard deviation that is being attributed to the blocks is 4.6, and the standard deviation that is being attributed to the error of the model, so the error that we always have, is 0.38. So we can see here how blocks have a huge variability, especially compared to how much is being left as a residual error of the model. So blocks are really, really variable in this case, and that's the standard deviation that is being attributed to blocks in this case. And then when we come to the fixed effects part of the summary, we see that now the rep that was showing before is not here anymore, right? It's been moved up to the random effects part of the summary. And now the fixed effects only have our sitting rates, and they're all, at least those estimates are all significant. But this is not the ANOVA yet. So well, before we go to the ANOVA, let's check the residuals. So let's see here. Let's just copy the name of this model, get down here and do the plot so we can look at the residuals. And so because it is a mixed effect model, and we asked for the plot function, it only gives us the standardized residuals over the fitted, which is the first plot that we've been seeing up until now. It did not give us the other 3 plots that we were seeing before. And this is, again, by design of how mixed effect models are being treated and are being interpreted by the plot function. That we're not going to get into that. And for sake of time, I'm not going to even create the other residual plots. We're just going to stick with this, okay? So, I mean, just looking at this plot, it looks pretty good, right? I mean, we don't see a strong pattern, so the points are kind of like randomly scattered, and we don't see anything really crazy high or crazy low. They're all, okay. So just looking at this, I would say good to go. All right, so now let's ask for our ANOVA table, ANOVA uppercase. We use again the name of the model object, and we say type equals 3. And we see that just like before, when we treated blocks as fixed, well, I mean, the difference here is that, so when blocks were fixed, we had a wrap row in our ANOVA table. Now that is not here anymore, and that's because ANOVA table, in this case actually deviance table, only assesses the effects of the fixed terms in your model, right? And the only fixed term in this current model is sitting rate. So that's why we're not seeing the wrap here, but we see that sitting rate is still highly significant. Okay, so let's get the means. I left you with the code there, so you didn't have at least to type this part of it. You can just run it. Don't forget to run it because we're gonna use it for plotting. And then we're gonna do the COD again that I didn't write for you, so we're gonna have to type together. So we use that RCBD rand underscore mod object, comma, you know, we say reversed equals true, adjust equals none, letters capital L equals to letters lower L, and then we add a pipe. We say as dot data dot frame, and then we do that mutate on the letter. So we say letter equals trim WS for trim white space dot group. So this is what it should look like. We can let's see, what did I do wrong? Maybe I didn't run this properly.
No, I think it is the RC brand underscore means.
Oh, do I have a? Oh, yes. Thank you, Andre. Perfect. Yes. Yeah. So I use here the model object, and that was a mistake. I should have used the means object, which we just created above. Perfect. Thanks, Andre. So this should work now. And then we have the letters. Okay, so let's do this. Let's make the final plot, and we're getting to the end of today's workshop. So I guess we're kind of on time to really look at this plot here. So let's just work on that plot, and then I'll have you compare some points here between the blocks fixed and blocks random. So to make this plot, again, we do use ggplot. We bring the RCBD rand underscore COD. We say, oops, aesthetics, X equals factor sitting rate, Y equals EM mean, and then plus geom point range, aesthetics, Y min equals to EM mean minus SE, Y max equals to EM mean plus SE. And then I will add plus geom text and do aesthetics function, label equals letter, comma, Y equals EM mean minus 0.5. And I'm gonna make this plot. Okay, so this is the perfect point that I want to call your attention, okay? I'm just gonna pop up this plot because I want to roll up on the script, and I want you to look at the plot that we did blocks fixed. And that's gonna be a very, very important part of our comparison. Okay, so let me actually pop both of them out. Hopefully that's gonna work. Yeah. Because I want you to look at them side by side. Okay, so I don't know if you can really tell, but I will tell you what I'm seeing. if they were on the same Y scale here, as far as minimum maximum, you would see that the means are exactly the same. And again, on the left, we have the fixed effect block. On the right, we have the random effect block. Okay, so you're not being able to tell by how the plots are being shown, but the estimates of the means are exactly the same. If you look at the letters, they're exactly the same. So DD, CC, BB, AA, exactly the same. The only difference here is the error, the standard error associated with a treatment mean. This standard error here is larger when blocks are random as compared to where blocks are fixed. The same data set. Remember, this is the same data set, just on the left, blocks are fixed. On the right, blocks are random. The only difference, so okay, well, let me just stop there, take one step back. When you have a balanced RCBD, like we have here, so we don't have any missing data, you don't have information, let's say you don't have incomplete blocks. What is an incomplete block? Is when you do not have all treatments at least once in all blocks. So let's say, and there are designs that are incomplete block designs, and that exists, is one type of design that is available for us, which is not the case here. This case is what, at least in field studies, is the one that I've seen the most, where you have RCBD that is a complete block where treatments appear, every treatment appears at least once in every block, and you don't have missing data. In this case here, the only difference between treating block as fixed, as in the left, to treating block as random, as in the right, is the standard error of a treatment mean. There is no difference in the mean itself. When you do pairwise comparisons, the mean difference, standard error, is not inflated. And we can see that because the letters are the same. The only thing that's different is that on the single treatment mean, the standard error of that mean is inflated if you have random blocks. And that's basically because the way that the math happens behind the scenes is that the standard error of a single mean that is being shown on the right actually has the error of the block plus the error of the study, of the residual. Whereas on the left, where blocks are fixed, it's only incorporating into that standard error the error of the residual. Because it does not have an error for block, because block is fixed. And again, the only difference is on that single treatment mean standard error. Because when you compare one treatment to the other, the block variance cancels out, and it does not impact the significance of the comparisons, which means it does not impact the letters that we're seeing here. Only difference. So if you think about it, if you wanna have blocks as random, just keep in your head that if you're gonna show the standard error of the mean, in this case, we're showing that in both plots, if blocks are random, that will look very, very large. And it's not really representative of the variability that was taken into account when conducting pairwise comparisons. So the plot on the right, which is the random effect block, just looks highly variable because it's incorporating both of those sources of variability. But when the comparisons were made, this variability was actually canceled out because of the paired nature of the variability. Only difference, that's it. Okay, so let's see, let me get back where I was before. Okay, so I just want to give you some final considerations on block, on what should you do, or I mean, you do whatever you want, but if you want some advice, what I think you could do in your analysis. So there is this paper here by Dixon. He's a statistician from Iowa State that he published, Should Blocks Be Fixed or Random? And what I told you is exactly what I learned from his paper, and I basically replicated with this data set that we're playing today with, which is this. So estimated treatment means are the same if blocks are fixed or random. The difference or contrast among treatments, the same. Error variance, the same. The estimated standard error of treatment differences, the same. So the inference with the intervals for differences, the same. The only difference between treating blocks as fixed or as random is the standard error of the treatment mean. So not mean differences between treatment 1 and 2, but the treatment alone, a single treatment, that standard error is the only difference between treating blocks as fixed or random. If you have a regular RCBD where it is a complete block and it does not have missing data. So Dixon, I can share this paper with you if you want to read. He does some more statistician-like simulations to prove this, and it's a really nice paper to read if you really want to understand more about it. But if you just want the overall picture, he gives some recommendations, and I added one of my own based on what I've seen here for you. So if you have a regular RCBD where all treatments appear in all blocks, so balanced blocks, no missing data, and the number of blocks is less than 12, which is most cases in ag, and you're not using this model for prediction, then treat blocks as fixed. And why do I have this last part here that I added myself if you're not using the model for prediction? We're going to see more about why this is important tomorrow when we will be creating prediction regression models and predicting. Now, point 2. If you have intra-block information, and what do I mean by that? It means that the information that one block has is different than the information that block 2 has. And that happens because you have different treatments in different blocks. So that means you have intra-block information that you need to extract. So if you do have intra-block information, maybe because you have unbalanced blocks or because you have incomplete blocks, and the number of blocks is more than 12, then you can treat as random. And that's going to help you to extract both the intra and inter-block information if you treat as random. If you treat as fixed, you're just extracting, I think, the intra-block information. And the third point here is if everything said in number 1 is true, but the model used for prediction, then you can treat as random, because then that's going to help you to use the formula to predict. Okay, so this basically it wraps up the block fixed, block random conversation. Now, I do want to do one last thing before we depart, which is something I promised you in the agenda, which is to create a publication-ready final plot. This is finally the point where we're going to create a plot and export a plot that could go right into a manuscript, and it would be publication-ready. So I just want to do this kind of with you guys. So at this point, if you're still following along, feel free to just shout out if you think of something. And the first question, so you don't have to use the chat for this. You can just speak up if you want. The first question that this final publication ready plot is something we're going to do together. I don't have my own code for this. I don't have on my cheat sheet here. And I want it to be that way because I wanted us to work together. So, excuse me. So first question I have for you. Which of the analysis, so if this was your study and you had conducted a proper RCBD, which of the final results would you like to show on your paper? Would you like to show the one with blocks as fixed or blocks as random? Anyone can, I mean, if you don't want to speak up, you can just write that down in the chat as well. But I just want to feel your thoughts on that. Okay, so Melinda said fixed. Anyone else want to weigh in? Okay, I don't hear anyone. I'm not seeing any text. So I agree with Melinda. I would choose the fixed analysis. And the only reason why is because the standard error bars on the means is not misleading when we're comparing the errors with the letter separation. So I agree with Melinda. I would use the fixed one. So let me just, let's see, where do we have that? So heterogeneous, corrector, CBD, blocks fixed. So it would be up here. It would be, I mean, we can just basically copy this. So I just went back to line 359. I did that by coming up here on the table of contents. So number 7 is where we ran the heterogeneous experimental design, corrector CBD, blocks fixed. If you just browse to the final plot, which is the G, so 7G is where I am right now. If you just click there, it's gonna take you there. I just copied this ggplot part here. And I'm just gonna go all the way back down so we can just paste that here so we don't have to be typing again. All right, so I'm just gonna print it, all right? And this is what we have right now. So this is where the teamwork is gonna come into play. How do you guys think, or what do you think we should change in this plot before we can put this in a paper? You can just write in the chat if you want, or if you want to speak up, feel free. What should we change about this?
Your AGSA labels are going to need some work there for sure.
AGSA labels, perfect. I agree. All right, so let's work on that. So to do that, we do plus, we do the labs function, and inside the labs function, we can call, let's say, x first. Let's rename the x-axis. Right now, it's just factor sitting rate. I mean, it is that thing, right? Which is very not intuitive, and it would never be published that way. So let's call it seeding rate, and then open parentheses. Let's say like 1,000 seeds per hectare. Okay, so that sounds okay for me. And then the Y would be yield megagrams per hectare. All right, so let me just run that. Okay, that looks a lot more professional. That looks awesome. Okay, what else do you guys think we could do here to make it look nicer? Or is it good enough? I mean, it could be good enough, right? Any more thoughts? I don't know.
Leo,
Yes.
we may change the font family.
Nice.
In Fastget.
Okay, so I don't think I've done that, but it's probably on the theme.
Uh-huh.
Do you remember the argument?
Yeah, here you can put text.
Mm-hmm.
Equal element text.
Mm-hmm.
And then you put family.
Okay.
And then you name the family. For example, you could say times or
Times.
I think
Awesome.
times in Mac will work.
Let's see. Nice. Yes, we did it. We changed the font. And it's nice because it changed all the fonts, right? It was like everything that had a letter changed. Well, I don't know. Maybe the actual labels
Not
didn't
those ones.
change, but yeah, but everything else changed.
If you go before theme and you put, for example, a theme BW or something,
Mm-hmm.
and then you put, I think that the code is base family. You put theme underscore BW and then open, and then you put base family.
Oh, I see. Base. Yes. And then times.
Oh, yeah. Let's see.
Let's see.
A plus. You're missing.
Yeah, nice. So yeah, this is super nice. And before we actually show that, I just want to show people something else before we do that. So if we just run up until here, we're basically seeing the theme that is the default theme of ggplot, which if you see a plot with a gray background and white lines, it's probably ggplot, coming from ggplot, because that's a default. If we want to change like the overall feeling of this plot without having to think too much about it, there are a whole bunch of internal theme options. So we would do like a plus, hit enter, you start typing theme, and then you do underscore. So all of these are different options that ggplot itself gives you. And there are other packages that even extend the options of themes that you can use. So the one that Adrian just suggested us to use is the BW. So look how that's going to change, right? So now it's kind of gray background, and BW, which stands for black and white, is going to give us this type of theme, which is a very nice theme. I use this one a lot as well. And then I just want to give you a taste of some other themes that are very different, just so like the dark is very different theme, right? It's like a very distinct from the others. And you can actually play with all of these themes that you get after you type theme underscore and you just hit tab. There's a whole bunch of them. And you can even increase this list if you download other packages, if you install other packages. But so, and this is, I just wanted to tell this before we actually, use the suggestion that Adrian had with the theme. So we use theme black and white, and then we also changed the base family, or the base fonts that the package uses, which we changed the times. Awesome. So I just want to, well, let me leave it to you guys. Do you think, would you like to change anything else, or do you think this is gold for a publication already? I think it looks okay. I would just change some aesthetics, but just for being playful, not because it needs it. It's already awesome. Does anyone have any? Oh, go ahead.
I was just gonna say, I guess it's kind of a personal preference, but I know some people like to make sure the origin is included in some way, like on your scales of your axes.
Yes, perfect. That's a great point. So what we can do here then is, so Brian was saying that we should add have the origin on the scales, and that's really important because sometimes if you don't pay attention to the origin of your, or if you don't pay attention to the range of your y-axis especially, it can be very misleading, right? You can take a very small difference and make that seem huge, and that's a great point. And some reviewers actually don't like the plots the way they are right now because they want to see that starting at 0. So for us to do that, I'm just going to come here and say scale y continuous. And then inside of this function, it has an argument called limits. And we can just say where it starts and where it ends. So 0, and let's say 15. Yeah, awesome. So we see how now, like, the difference, and this goes again back to the point that when you see the origin of the plot, the differences don't seem as different as when you compress that y scale. So that's a really great point. Anything else? Any other thoughts? So I can't see the chat for some reason. I misplaced it. Oh, there you go. Let's see if somebody's saying something there. Okay, somebody said about the range. Adjust the function, find the optimal rate and maximize. Yeah, okay. So main title, we can give a main title, groups color, axis label and units. Okay, a whole bunch of great stuff here. Thanks, guys. So I will. I'm just reading some comments here. I will share the code after the end of the second day. So after tomorrow, I will share both codes with everybody. Just saw that. So somebody said give different colors to different groups. We can certainly do that. I really like playing with different colors. So let's just come here and say, so inside the AES function, of the ggplot level, we can say like color equals, and then we say what variable we want to color that by, if that's what we want to do, right? If we want to give a different color to each rate, so we can say color equals the seeding rate, and we can also do fill equals seeding rate, because color and fill are two different things that go kind of together. So there we go. We don't really need this legend because it's, I mean, they're not really explaining anything that's not already in the plot. We know that those colors are coming from the different rates. So we could just hide this legend. So we can say legend position equals none, and then we just remove the legend. And we could, you know, change to different colors in here. Let's see if there's one like scale, color. We have a whole bunch of options. Let's see if there's a nice one. There's really not one that I like. So I'm just gonna leave it like that to not make things more complicated. So let's say, you know, somebody asked you if we could show the actual variability of the data. And that is a great question. That is something that I usually like doing. So what I usually do is I combine the raw data box plot data that we saw like in one of the plots. And then I bring in the letters from the actual analysis and combine the raw data box plot with the statistical analysis letter separation in the same plot. So we can do that. I mean, we would have to change. Well, I don't want to keep you guys for too long, so that would take, I don't know, a minute or so to do. But we can look into that tomorrow. So all right, let's say that we looked at this and we think it's ready, right? We could change a whole bunch of other stuff about this plot that we could go forever. So let's just call it good and say that we have it in the way that we want it. Now let's save it. So you come to the end of your ggplot code, you just add a plus, you write the function ggsave, open quotation marks, open parentheses, open quotation marks, have your cursor in between quotation marks. Remember, right now, if we hit tab, we are inside the markdown folder. So we want to get a level up. So it's use .. And then I normally save all the outputs, including this one, into the output folder. That's what it's for, right? So things are organized. So we put it there. I'm just going to give it a name. So we can call it, you know, let's say rand, oops, I'm not seeing this. RCBD rand COD. And then you say dot, and then you can say what is the extension of this plot that you want to save as. Normally, I save either as PNG or as TIFF. And then we can just save it. I saved as TIFF. And then if we slide here to the right and we go on the output folder, now this plot is there. And if we launch it, we're going to be able to see how it was actually rendered in the save file, right? So let's say I think it's like, I just want to change the dimensions of this plot. So I can come on ggsave, I can use the width function. I usually use width 6 and then height 4. I think this is in inches. And then I just want to open that again. Now it looks a little bit more compact. For me, this is a perfect size. So there we go. This would be that publication ready plot that I just wanted to show you guys how we would have done it. And let's see, I just have very, very quickly some thoughts here for you before we finish up. So like 5 minutes, I'll be done. So something very important, that after we went through, like, you having the right design and you having the right analysis, right? What does that mean then? Well, the best design will always be the simplest one that will account for the uncontrolled sources of variability that may come from a heterogeneous experimental design. So does that mean that RCBG is always better? No. CRD is a better design if your material is homogeneous, because as Adrian very, very, very nicely pointed out, if you can do a CRD and you do an RCBD instead, you're losing power because you're taking up degrees of freedom from the error to estimate the block effect, which was not significant. So CRD is the better design if your material is homogeneous. On the other hand, RCBD is better than CRD if you have heterogeneous material. And we saw this on the simulations and analysis that we did, where running a CRD with highly heterogeneous experimental material just gave no treatment effect that we could find. And this is also something very important that I wanted to touch base, is that experimental design is something that we have to plan before installing the experiment, right? So you go out, you take soil samples, I'm in soil fertility, that's what I would do, where you would look into, like, do we have, so if it's a study that we're evaluating fertilizer, do we have different levels of the nutrient that we're trying to test across the field? Are those levels very different that we should control for those differences? So you have to really try to understand what type of natural variability you could have in that area that would interfere with your treatments. So it could be fertility, it could be water management, it could be soil texture, it could be slope, it could be a whole bunch of things, organic matter. I mean, we can just keep going, right? That could be affecting. If the variability in one of those variables is very large, we should plan that study ahead of time to be an RCBD and to block properly. We cannot do a CRD and then find out that we have high variability and then treat the reps as blocks. It doesn't work that way, because the whole principle is that you identified where the variability was and that you blocked in such a way that you randomize within each one of the blocks. If you run a CRD, you are not randomizing within a block because you don't have a block. Right? So you cannot play and plug as far as I planned one study, but I really analyze as if it were something else. We cannot do that. We should not do that. And if we have balanced RCBD designs, treating block as fixed will be the correct choice most of the time. I can share with you guys the paper that I used to understand this as well, and so we can read on our own and understand this better. And the last point that I have here is, if you've been able to follow along, and even if you have not been able to follow along to the end, you can want to invite you to click on this preview button here. So this R Markdown file is a notebook file, which means that it has a preview for us. If you click on preview, I hope that in your machine, you're going to be able to see what I'll see on mine. It's taking, it didn't pop up immediately. I think it's thinking, it's compiling things to show me, but after it's done, it's gonna create an HTML file. Okay, mine is coming up, where everything that I wrote in that R Markdown file is right here as a report. Everything that I wrote as comments, all my code, all the outputs that we had. So it could be a table, it could be a plot, everything is here. So comments, code, and plots. And even if you want to hide code, let's say you're sending this to your advisor and they don't really know R or don't care about the code, you can just come on the top there and say hide all code. It will hide the code and just show you your comments and the output. So this is a super nice way and reason to be using R Markdown and R notebooks, because if you're doing your analysis as you're already doing anyways, you can create a reproducible report right off the bat without having to do much more of anything to get it done. Okay, so this was all I had. Tomorrow we're going to be comparing regression with ANOVA and then using regression for prediction and for estimating the optimum level of a given input that maximizes yield. So thank you guys for staying with us till the end. If you have any questions, I'm going to be here for the next 10 minutes. And if you don't, I hope I didn't lose you today. Hopefully you're able to follow along. If you have any feedback about today, I'll be glad to hear it. I love to hear feedback, good or bad, regardless. And if nothing else, I'll stay a little bit longer just if anyone has questions. And if not, I'll see you tomorrow, the same time in same link, I guess.
All right.
Thank you, everybody.
Thanks, Leo. That was great. I think everyone learned a lot. So this workshop was recorded. So I will just finish recording the workshop right now.